Okay, so last time we proved we sketched the proof of Manin-Mumford conjecture for a curve in the square of an elliptic curve, and I had two ingredients that I didn't prove. One was what we called X Lindemann Weierstrass. So this was a functional transcendence result, and that told us about kind of algebraic varieties lying in the pre-image of under the exponential of an algebraic variety, and the other was what I called Gower Bounds, and that said that if you have a torsion point of order n, then its degree is relatively large in terms of n. So today, in the last lecture, I'm going to sketch some of the ideas for proofs of both of these using counting. So these can, in the context that I'm talking about, both of these things were known already, proved in other ways, but you can prove them using Pila-Wilkie or variations on Pila-Wilkie, and that's important for kind of more general things, although I won't talk about that. Okay, so I'll do Act Lindemann first. So just erase this. No, I didn't want to erase that. Press that. It's really magic stuff. Okay, so what do we have? We have A in abelian variety of dimension G. Find over the complex numbers, and if you don't know what that is, we just take A to be e to the g, where e is an elliptic curve, which we saw last time. We have its exponential map. Now, if you're in this, if A is e to the g, then pi is it's given, well, I'll just give its affine part. It's given by p of z 1, p prime of z 1, well, up to p of z g, p prime of z g, where p is the Weierstrass p function we saw last time. So I think last time I called pi was just in one coordinate.
Gareth,
yeah,
your domain and target are wrong. I think
the wrong way around. Thank you. Thanks. I have V, a complex algebraic subvariety of A. And then, so I can pull that back under pi, and we suppose that in there we have a maximal irreducible complex algebraic subvariety. So maximal means that if you have another irreducible complex algebraic subvariety of pi inverse of v containing y, it is y. And then with these conditions, the X theorem, well, the Lindemann-Weierstrass part of X says that then pi of y is a translate for abelian subvariety. Okay, so So what's the idea for the proof? The idea is that this condition here is going to mean that y meets lots of fundamental domains for the lattice. So that omega is going to be the kernel of pi. And the fundamental domain is just a it's just a fundamental domain. That's like a parallelogram. So if you're in C, you pick some choice of basis vectors, these ones. Maybe a good picture. So this is a fundamental domain here, and then this y is going to meet lots of these as it moves around in C to the G, and we're going to detect that using a definable set. And fundamental domains correspond to lattice points because you move them, you fixed a fundamental domain, and other ones got by moving your fundamental domain by a lattice point. And a lattice point is almost an integer point, and we'll use Pila-Wilkie, so you can then change coordinates to get integer points, and we'll use Pila-Wilkie. Well, you show that there's lots of integer points, and then Pila-Wilkie gives you a semi-algebraic set, and we'll show that that leads to a big stabilizer for your y. So let me write down a bit more, and then because I'm not going to give the whole proof, I'm just going to show that there's a big stabilizer. So so using definability and Pila-Wilkie, we show that there's an infinite semi-algebraic set S such that y plus S, so all the translates of y by points in my semi-algebraic set, is equal to y. So that means that the stabilizer of y in C to the G is big. It has positive dimension. And then that will imply, although I won't show that. So this implies that B, which will be the stabilizer of V. So V is the thing on the abelian side. So B, the identity component of the stabilizer of V also has positive dimension. And then you quotient out on each side. So on C to the by the stabilizer of Y, and A you quotient out by the by B, and you replace Y and B with their images under those quotient maps, and you show that if the stabilizer of the image of Y had positive dimension, you do the whole argument again, you get a contradiction. So the image of Y is a point, and that's what you translate your abelian subvariety B by to get pi of Y. So I'm just going to say that then quotient out to finish. So I'm not going to give that part of the proof. I gave a reference last time, but I will show this bit because this is where the counting is used. Okay, so what do? We've got our omega, so we fix a z basis. of omega. And we'll use that to identify c to the g and r to the 2g. So then points of omega will correspond to integer points. And then we get a height on points of omega. Now fix a fundamental domain. So in these coordinates, we can take just 0, 1 to the 2g. Now let sigma be the points in c to the g, such that when I move y by that point, it has non-empty intersection with my fundamental domain. And it's contained in the pre-image of v under pi. Okay, so this is the set that's going to detect like y being in lots of fundamental domains. So we want to show that sigma is definable in Rn. Okay, so to see this, I'll show that it's equal to something else, which is clearly definable. So let sigma prime be the z in c to the g, such that y plus z intersect f is not empty. And we have this after restricting, after intersecting with the fundamental domain. Okay, so, and y plus z intersect f is contained in pi inverse of v intersect f. So, so sigma is contained in sigma prime, and sigma prime is definable in Rn. So why is it definable in Rn? Well, this condition here is semi-algebraic, but pi restricted to f is definable in Rn because it's a restricted analytic function. It's almost, it's a restricted meromorphic function, which is as good. So once you intersect with f here, you can talk about this in Rn. So, and sigma prime is definable in Rn as pi restricted to f is definable in Rn. Now, if you have z in sigma prime, what do you have? Well, you've got this. This is a non-empty open subset of y plus z. And on that open subset, these equations hold, the equations that say it's in pi inverse of v, and y plus z is irreducible. So by analytic continuation, those equations hold on all of y plus z, and you have this. So if z is in sigma prime, then y plus z intersect f is a non-empty open subset of the irreducible variety y plus z. And then since y plus z intersect f is contained in I inverse of v, analytic continuation implies that y plus z is all contained in y inverse of v. So certain sigma, and so sigma is definable in Rm. So next we want to show that it has lots of integer points. So given a lattice point, let h of omega be its height with respect to the basis we fixed above. So we'll show that there's an h0 such that if I have at least h0, the number of points in sigma, which are also lattice points of height at most h, is at least h over 2. Sorry, h, not h0. So that means that this does indeed have lots of lattice points in it. So for this, let gamma be a continuous map with image that's unbounded. Why? So gamma exists because y is an algebraic variety in C to the G, and it's path connected. So I can just take some curve in it that has unbounded image. Now, as that image crosses from one fundamental domain to another, the two periods associated to those fundamental domains, like in the well, you will see what I mean. The two periods that you get the fundamental domain by translating from our original fundamental domain by a period. Now, if you move from one to another, the two associated periods, their height differs by at most 1, because like they can only differ by you can't have like a coordinate where it goes up by 2 because you'd miss a fundamental domain in the middle. Let me try and say that a bit better. So as the image of gamma passes from a fundamental domain so there's something in chat, just a sec. Isn't it h0 over 2? No, this is correct. Because I want to have a relatively large number of points. If I had an h0 here, h0 is a constant. So this would just be a constant, whereas I want something that grows. I mean, it doesn't have to grow almost linearly, but well, linearly. It would be enough if it just grew like h to the epsilon, but in fact you get this. Okay. Good. Okay, as the image of gamma passes from a fundamental domain f minus omega to another, f minus omega prime, the heights of omega and omega prime differ by at most one. So if we put theta to be the omega in omega such that the image of gamma intersect f minus omega is not empty, then when I take the heights of the elements of theta, that's an interval in the integers. H of theta is an interval in the integers. Now, gamma's unbounded, so this interval contains arbitrarily large integers. So it contains, so h of theta just contains something like this. Now if I take a lattice point, then so our variety y is contained in pi inverse of v, but pi inverse of v is invariant under lattice points. So y plus omega is also contained in pi inverse of v. Because pi is periodic with respect to omega. So sigma intersect omega is really just omega such that y plus omega intersect f is not empty, because the other condition is automatic for lattice points. And so theta is contained in it. Okay. So that gives us our this. Now by Pila-Wilkie, that means that sigma must contain an algebraic curve, a semi-algebraic curve. S contained in sigma, and there's some period. We can assume that there's some period in it. So we have, so because S is contained in sigma, that means whenever I add something in sigma to y, I stay in the pre-image of v, and so I get y plus s contained in pi inverse of v. And so y is contained in y plus s minus omega. It's contained in the pre-image of v. And now this is a semi-algebraic set here, and just like in the proof last time, when we had a semi-algebraic set, we could it contained, well, we need some conditions on it, but when it's contained in an analytic set, you could replace it with an algebraic set rather than a semi-algebraic set. So a bit like last time, we get a complex algebraic y, y prime, sorry, with this. And then by our maximality, these are equal. Okay, and that's what we wanted to show. And then, yeah, so the rest of the proof after that is kind of general stuff about abelian varieties. I won't go into it. I was going to just stop with that proof. But if you didn't like that, then the next application is quite different. So don't worry. So the next application is the Gower Bounds. Okay, so I guess I should, these ideas are due to Jonathan Pila. So this proof is contained in his paper on Andre Ork for C to the N. And what's important about this proof is that it works in other settings, not just abelian varieties, whereas some of the other proofs of this kind of result, well, at least then they didn't work in other settings. It's possible they do now. But, yeah, okay. So Gower Bounds. So the idea for this proof is due to Harry Schmidt. And again, so what we're going to prove here was known already by other methods, but these methods generalize in a way that those other methods don't yet. Okay, so what do we want to show? We'll show the following. So this is due to massa. Well, this is a weak version of a result due to massa. Suppose E is an elliptic curve over a number field. Okay. Then there are C and delta, such that if I take a torsion point and it has exact order n, then its degree over k is large. Okay, so this is what we want to prove. So Harry's idea was to use counting to do this, but it seems you can't, it's not enough to use Pila-Wilkie. Pila-Wilkie is not quite good enough, so you need an improvement. So for the improved version, we need Pfaffian functions, or we can use Pfaffian functions. I guess we don't need to. But, so a sequence F1 up to FL from U to R have analytic functions on a product U of open intervals. U is in R to the N, is a Pfaffian chain. If it's derivative, as you go along, the derivatives depend polynomially on the things you've already got. So if there are polynomials Pij in n plus I variables, such that when I differentiate fi with respect to xj, we use Pij x and then f1 up to fi. So you have a triangular system of differential equations. So for instance, say x is a Pfaffian chain on its own. And it's not hard to show that like log lives in a Pfaffian chain. Or if you restrict sine to something like 0 pi, that lives in a Pfaffian chain. Now, it's a theorem. Oh, I have to give it a name. Let our Pfaff be the real field expanded by all Pfaffian chains. Like this, where their domains U have to be taken for what I'm about to say to be true. And then Wilkie proved that our Pfaff is O-minimal. So we have the Pila-Wilkie theorem here. But as I said, that doesn't seem to be quite enough. So instead, we'll use the following. So this is due to me and Margaret Thomas, except it's not, I'm going to state it in a form where it's modified in a way that Schmidt did. So what's it say? Suppose X is a surface that's both existentially definable in our Pfaff and definable in our So for instance, if you only need Pfaffian functions restricted to compact boxes, then this will be true. But something like the exponential function, well, or rather, I mean, X is a surface, but you couldn't use the unrestricted exponential function in an essential way in the definition of X. And there are C, K, and L such that for all D at least 1, H at least E, a number of points on the transcendental part of degree most D, height at most H, is less than or equal to C times D to the K times log H to the L. So in the version that Margaret and I had, we didn't have this here. We just counted points whose coordinates lived in some fixed number field. And Harry, like he observed that the proof just gives this as well, really. So what's the what's this doing? What definability in the Rn gives us a mild parameterization. So what our theorem actually said was if you're existentially defined in R Pfaff and have a mild parameterization, then you get this bound. But you just get that automatically if you're defined with Rn. So I won't say what a mild parameterization is, but it's a parameterization where you have a parameterization by C infinity functions. You have a certain uniform bound on their derivatives, but it depends on the order of differentiation. It's not just one like it is in an R parameterization. But this is the kind of thing that helps if you're trying to prove bounds like this. So perhaps you've seen Siegfried talk about that in the introductory workshop. Okay. Oh yeah, you could put Rn with all power functions here as well. You'd still get that. Okay, so from the proof of Manning-Mumford, we had this we had a function b like this, which was real analytic. So this is just pi in the switched coordinates, where you make a real change of coordinates on C. And so with torsion points on E corresponding to rational points here, and as we observed in the proof of Manning-Mumford, B is definable in Rn. So I can think of this as living in C2, because I'll take away the origin. And then B has coordinate B1, B2. So then we need a theorem telling us that the other condition here holds, right? We've got divinability in Rn automatically. So this is due to McIntyre. And then it was developed by me and Harry. So if I take gamma to be the graph of B1, then that is existentially definable in R5. So really, this is just due to McIntyre, but what we did was show that you kind of have an explicit definition in terms of Pfaffian functions, and the complexity of that definition doesn't depend on the lattice at all. It's completely uniform in the lattice, which is useful for other things. Okay, so then we've got, with this, we've got it's definable, existentially definable in R-Pfaff, definable in Rn, so we get a counterbound like this. So corollary. The number of points on the transcendental part of gamma have degree at most D, height at most H. It's bounded like this. Now, okay, so in fact, the transcendental part of gamma is everything. So why is that? If you had a curve, so I won't write this bit down, I'll just say it. If you had a curve, it's an algebraic curve, S lying in gamma, then just like we've done already, you'd get an algebraic, complex algebraic thing that intersected gamma. You'd have to restrict it a bit to get into gamma. But then gamma and your restricted algebraic curve are both analytic sets of dimension 1, so they'd have to coincide somewhere. But that would contradict the transcendence of the Weierstrass B function. So actually this holds on all of gamma. Okay, so now let's take a torsion point. Exact order n, and take A, B co-prime to big N such that sorry, B of A over N, B over N is the x coordinate of B. Because we've only taken the first coordinate B, so B1 should be. So this is what we used in the proof of Manning-Mumford, that rational points here correspond to torsion points, and that the rational points corresponding to a torsion point of order n have height n. So that's why these exist. Now I said this before when I started talking about heights. If you have a root of unity, if you look at the definition of height, it had some maximums over the conjugates of your alpha. Now, if alpha is a root of unity, all the conjugates will have absolute value 1, and that whole product will be 1, and you'll get height 1. And in fact, if alpha is a non-zero algebraic number with height 1, then it has to be a root of unity. So the roots of unity are exactly the algebraic numbers of height 1, apart from 0. And there are heights on elliptic curves which have a similar property. So you can put a height on your elliptic curve over a number field with the property that torsion points in that height have height 1. And then sort of general theory of heights tells you that that height on the elliptic curve differs from, well, it implies that a torsion point will then have bounded height in the normal sense of the height. So I'm just going to say theory of heights implies h of p is less than or equal to some c prime, where c prime is just a constant depending on e. But not n, that's the point. So what do we get? So that means that this here is a point of degree, let's let d be the degree of p. Then a over n, b over n, x of p is in our set gamma. I guess c prime n. So this point here is a point of height at most c prime n, because you've got some n's here and a c prime coming from this. And these are rational, and this has degree at most d. So you get a point like that. But then you get lots more. Now consider the points. Well, p, 2p, 3p, up to n minus 1p. Right? So each of these has a corresponding rational pre-image. Of height at most n. So each of these leads to a point in here. And they're all distinct. So what do we get? So we get not quite all distinct, because I haven't distinguished the y coordinates, but at least half of them are going to be distinct. So we get something like the number of points on gamma is less than or equal to our polylog bounds, so it's like c2 prime d to the k log n to the l, and at least, I don't know, n over 3. And this gives d is at least some positive power of n times a constant. And this was the degree of the field we were interested in. So that's the proof of the Gower Bounds by counting. So that completes the proof. Okay, and I've got a couple of minutes left. So thanks for listening. And then I was going to, I want to share something on my computer. I'll have to switch. And I was going to finish with some advertising. So if you want to learn more about applications of O-minimality and number theory, there's a summer school this summer in August in Oxford, which hopefully will be in person. That seems difficult to predict. But yeah, if you're interested, just email me to find out more. We'll go to this link here. Copy that. Put it in chat. Okay, thanks.
Thank you, Gareth.
Sure.
And so, Gareth, we'll have a question session next week on Tuesday at 11:10. So prepare your questions for Gareth.
I stopped the recording.
And there's a seminar now, right?
Exactly.